Have you ever stopped to wonder how we actually keep track of energy in something as wild as a jet engine or a massive power plant? I mean, these are systems where things are always moving, always flowing. It's a really cool puzzle. So let's just dive right in and unpack the physics that makes it all possible. So this is really the big question, isn't it? How in the world do you balance the energy books for these things? It's not like it's a sealed box where you can just, stick a thermometer in it. Here, both the stuff, the mass, and the energy are a moving target, constantly flowing in and out. Okay, so we all learned that one fundamental rule in science class, right? Energy can't be created or destroyed, it's always conserved. Simple enough. But trying to apply that nice, neat rule to a dynamic flowing system, well, that's where things start to get really interesting. The rule itself doesn't change, but how we do the accounting for it has to get a whole lot smarter.
To really get to the bottom of this, we first need to understand what we're up against. The main obstacle is in the very nature of these systems, and that means we need to get crystal clear on the difference between something that's open and something that's closed.
This slide just lays it out perfectly. A closed system, that's easy. Think of a sealed can of soup you're heating on the stove. You can put heat into it, that's energy crossing the boundary, but no soup is getting in or out. But an open system is more like a river. You've got water constantly flowing in upstream and flowing out downstream. And that moving water, that mass, carries energy with it. And that's the big complication we have to figure out how to solve. Now, don't worry about all the math on this slide for just a second. The most important thing here is that diagram up top. That process unit box, that's our stand-in for pretty much any industrial equipment. A pump, a turbine, a heat exchanger, you name it. This is exactly the kind of situation engineers face every day, with fluid moving in and moving out. And it's what we're about to break down. All right, so if we have mass flowing across a boundary, what does that actually mean for the energy balance? It's not just about the energy the fluid itself contains, it's also about the energy it takes just to move it. This leads us to a really crucial and, honestly, kind of hidden form of energy transfer. Just think about it for a second. If you want to get new fluid into a pipe that's already full and under pressure, something has to shove it in there, right? The fluid that's already upstream is doing work on our system just to make room. That's a real energy input, and we absolutely have to account for it. And on the flip side, as that fluid exits the system, it has to push on whatever is downstream to get out of the way. So now it's doing work on its surroundings. This is energy that is leaving our system. So you've got this constant push and pull of energy happening at the entrance and the exit that has nothing to do with heating or cooling. And this push and pull has a name. It's called flow work. It's basically the net result of all that shoving. It's the energy cost you pay just to keep the fluid moving through your system. You can think of it as the work the fluid does as it leaves, minus the work that was done on it to get it to enter in the first place. So you can probably imagine engineers and scientists looked at this and thought, keeping track of a fluid's own internal energy and this separate flow work thing, it's kind of a headache. So being clever and practical, they came up with a really elegant way to package it all together. And it really was a hassle. For every single pipe going into or out of your system, you'd have to calculate its internal energy, and then you'd have to calculate this separate flow work term. It was just messy, it was repetitive, and it cluttered up the main equation. There had to be a better way. Now, this is a really fascinating and deep point in all of thermodynamics. You can't actually know the absolute total energy content of a substance. It's kind of like trying to measure the absolute height of a mountain. High compared to what? To sea level, to the center of the Earth? You always need a starting point. So in thermodynamics, we always measure the change in energy from some agreed upon starting point, a reference state.
And this is the brilliant solution, enthalpy. It's simply defined as a fluid's internal energy, that's the U, plus its flow work, the PV. That's it. It's a thermodynamic property that's basically a total energy package deal. It bundles together the energy the fluid has with the energy it took to move it. So now this one term, enthalpy, tells you the total energy a chunk of fluid carries with it as it crosses a boundary. Pretty slick, right?
Okay, so now that we've got this incredibly powerful tool, this concept of enthalpy, we can finally put all the pieces together. We can build the complete, clean, and super useful energy balance equation for any open system. This is really the payoff for everything we've been talking about. We started with this complex, messy problem of flowing stuff. We found this hidden energy called flow work, And then we found a clever way to package it all up. And now we get to see the final result. And here are all the pieces of the puzzle. The total change in energy is just the sum of these things. And look, right there at the top, the change in enthalpy, delta H. That one term neatly takes care of both the internal energy and the flow work. Then we just add in the stuff we're more familiar with, changes in speed or kinetic energy, changes in height or potential energy, any heat we add or remove, and finally, any work from a physical piece of equipment like a spinning turbine, which we call shaft work. And this isn't just theory. This is the actual playbook. It's a practical workflow. You draw your imaginary box around the equipment, you pick your 0 point for energy, you figure out the change in that enthalpy energy package for all the stuff flowing in and out, and then you just solve the equation. It turns what seemed like a chaotic problem into a very straightforward step-by-step process. So, if there's one thing to take away from all this, it's that enthalpy isn't just some random letter in a textbook equation. It's a profoundly useful invention. It's a clever accounting trick that makes impossibly complex calculations manageable. It's what allows engineers to design and analyze almost every engine, power plant, and chemical factory on the planet. So I'll leave you with this thought to chew on. We've just unlocked the secret to tracking energy in all these dynamic flowing systems. So what else can we use this for? Could we apply these very same principles to understand the energy balance of an entire ecosystem, or a massive weather system, or maybe even the complex biological systems inside our own bodies? The possibilities are pretty much endless.